think there was a first derivative test yesterday. There'll be a second derivative test today. So what we're going to look at now is how the tangent line, how it changes. So before it was how the function changed. Now it's how the tangent lines, the cumulative tangent lines, how they change. So if the tangent line turns steadily in the counterclockwise direction, we say the graph is concave up. Let me go over here to this one. So right here, the slope, if I did a tangent line right at this point, the tangent line would be negative. It would be going down. It's fairly negative actually right here. It's really like going pretty steep down. But if I do a tangent line here, it's less steep. Here it's evening out. Here it's basically horizontal. Over here, the tangent line would be starting to increase. And when we get up here, the tangent line is getting really more steep up in a positive direction. Right? So we see how it is changing. It's very negative here, the slope, the tangent line. Less negative, 0, more starting slightly positive, more positive, and very positive. Right, so the slopes, continual slopes, are changing. They're becoming more positive continually. And when that happens, the tangent line slopes is really turning, so counterclockwise, this direction. They're turning in that direction as we go left to right. And we say that's concave up. Now, before I look at this, one thing students sometimes mix up concave up, concave down, so there's a little rhyme to help you. Concave up is shaped like a cup. The thing I also found out too is if you abbreviate it like C up, it actually spells cup. So concave up, yeah, so shaped like a cup. The other one is going to be if the tangent line turns steadily in the clockwise direction. So we're going this direction. Then we say it's concave down.
It's shaped like a frown.
You ruined it for me.
It's alright. Sorry, I had to put it up there.
I was going to say shaped like a clown, but frown works as well.
I don't get it. Oh, I was gonna say.
That's not it. I was trying to actually yesterday I was trying to think of other words that it could be. Clown.
Yeah, shaped like a. There's really nothing else.
Yeah, there's not much else. Just that's frown and clown. What other words rhyme with down? No, we won't do that. So right here, the slope is very positive. Right, it's going up. Here it's less positive. Less positive. Here the slope is 0. Here it's starting to be slightly negative, more negative, very negative. So the slopes are starting this direction, but they're turning in a clockwise manner around here. They're getting more negative. And so they're continually turning those slopes in a clockwise direction. And we say it's concave down, and yes, we say that it is shaped like a frown. So you wouldn't be surprised at how many students just mix those up. Even though, yeah, this one looks like it's probably because this one, it's like, it ends up. It's like a local max. But they think that means the up part, well, it's shaped up. So it's concave up, shaped like a cup. Concave down, shaped like a frown. Now, how are we going to find where functions are concave up and concave down? It's really looking at concavity and then the concavity theorem. So let's look at concavity. It's concave up. So I said it here, as the tangent lines are continually getting more positive. And yesterday, so the tangent line slopes. So the tangents are more positive. They're increasing. Tangent lines increasing. That's the definition. Concave up on an interval if f prime is increasing. F prime is tangent, right? Derivative, slope of the tangent line. Okay, now yesterday, if you remember, for increasing, the definition of that was when the function f, its derivative is greater than 0. Well, for concave up, we're dealing with the function f prime. So I have to change this to now f prime its derivative is greater than 0. So I'm plugging in f prime in place of f, because now we're dealing with tangent lines, not the original function. And so look what happens here. F prime prime becomes f double prime. And that's what the concavity theorem says down here. To find where a function is concave up, it's where the second derivative is greater than 0. And then as you can imagine, concave down is where f prime is decreasing. Decreasing yesterday was f prime less than 0, but now we're dealing with the function f prime. So I have to change this to f prime, its derivative less than 0. So it becomes f double prime less than 0, which is what it says down here. So yesterday it was first derivative test. We were doing f prime. We made a number line, checked them, and then looked at the intervals. And we plugged things into the first derivative. The concavity is the exact same. It is really the exact same, except second derivative. That's the only difference. And so we will plug things into the second derivative. So, again, this is where you got now 3 different functions you could plug things in. Concavity is always second derivative. So, we'll flip the page. We can try some examples. Any general thoughts on concavity right now? 7, actually. Thank you. Yeah, that's fine. And at the bottom, yeah, I don't think it's up here, but I just made, at the bottom of each page, I basically put a little summary, like, okay, for concavity, make a number line, plug x coordinates into the second derivative. All right, well, let's look, no other questions? Well, let's flip the page, let's try some. Well, it's a little blurry up here, but it's negative 1/3 x cubed plus x squared minus x. And so each function, well, let's determine the intervals of increase, decrease, and concavity. So what I'm going to show you, it's the exact same thing. It's the exact same thing except first versus second derivative. So let's try 2. One will be trig, one will just be a polynomial. Okay, so increase, decrease. This is f prime. So I'm going to do g prime for this function. So I'm bringing down the 3, I'm doing power rule. So it's negative 1/3, the negative will be there. 3's cancel out, and it's x squared. And then what else is there? X squared, so that's 2x, and then minus 1. Okay, so I really want to, we're just going to contrast this versus concavity. And you're going to see how similar these are. So this is yesterday, increase, decrease. We find the critical points, we set this equal to 0, and solve. Let's see, so I'm going to take out negative 1, so I can then factor this trinomial. Negative 2x plus 1. Yeah, so then it will work out. So negative 1, it's now going to be x minus 1, x minus 1. Squared minus 2x plus 1, yeah. So the negative 1 does not give us any solutions. The x minus 1 gives us x equals 1. Yep, it's actually a double root, double solution, but just for our purposes, we just get 1. Okay, so to find where it increases and decreases, that's the 1 x coordinate of our critical point. Just make a number line. So I'm trying to find increase and decrease, which is slopes, being positive or negative. So I'm plugging my values into the first derivative. So here's my test value of 2 and 0. It's number on the right of 1, number on the left of 1. Again, I'm plugging these into the first derivative. If I plug them into the original, that'll give me a y coordinate. That doesn't really help it much right now. So I'm plugging 0 in. You can plug them into any of those because they're all equivalent. I'll do the first one. So I'm starting with 0. 0 here would make 0. Plus 2 times 0 is 0. And then negative 1. We'll just make a negative number. If I plug 2 in, 2 squared is 4, and the negative was just on the outside. That's just negative 4. 2 times 2 is 4, minus 1. So this one's also negative. So by the way, I didn't ask about local max and min, but if it did, we would say there is no local max or min because it didn't change sign. So this function is decreasing and then continuing to decrease after 1. So let's write down increasing. Never. There's no positive up there. Oh, by the way, I'm going to cross off those test intervals so that you're not confused. We're done with those. There's no positive, it's not increasing anywhere. Decreasing where it's negative. Negative infinity up to 1, union 1 to infinity. Never brackets, always parentheses. So basically it's not increasing out, or sorry, it's not decreasing at 1, it's level at 1, slope of 0. So that was actually just increase, decrease. That was first derivative stuff from yesterday. Any thoughts on that? Watch how similar this is for concavity. It's not on this part. It's the same thing as the second derivative, exact same. So I do have double prime. Bless you.
Bless you.
Oh, it's G, isn't it? Let's see, so we're looking back up, the second derivative with negative x squared is negative 2x, and then a plus 2. We set it equal to 0. Hit solve. I could factor out a negative 2 if I want, or I could just add 2x and divide. I'll just add 2x. Divide by 2, so we get 1. This is not called a critical point. It's actually called a possible point of inflection, which I'm going to talk about in a minute. But we still use it just the same. So now I'm taking that 1. Oh, I put F. Yeah, I meant G. Well, no. So now I'm plugging this into the second derivative. I'm looking at concavity. You're always plugging values into the second derivative. And I need a value on the right of 1, which is 2, and 0. Okay, it happened to be the same as before, then x equals 1. So now I'm plugging these into the second derivative. Starting with 0. Plug in 0 here, it'll be 0 plus 2. So that's a positive. I don't need the actual number. When I plug in 2 here, 2 times negative 2 will be negative 4 plus 2, which is negative 2, a negative number. And so finally I write just concave up and concave down. It's the same idea as increasing, decreasing. It's an interval. So it's I'm going to get rid of my test values. Don't confuse me. Concave up, where it's positive. So from negative infinity to 1. Concave down, 1 to infinity. It might be good, but I'm going to just show you what it looks like on here. I know in general you won't be able to use a graphing calculator, but sometimes it can help right now just to see what's happening. Was that it? Just minus x? X squared minus x. Yeah, so you can see it's decreasing everywhere. Right at 1 it becomes level right about here. But then it is concave up. What do we find? Negative infinity up to 1. It's shaped like a cup right here. Okay? Now right here it stops. Like it's only the left side of the cup. Concave up right there. It would start to go, but it doesn't. It switches. And then here at 1 and on, it's shaped like a frown. So you might not get the full cup or frown. You might only get half of it or just part of it, but it does switch at 1 right there. So you can see this basically just helps us look at the shape of the graph. All right, we're looking at everything calculus helps us find out things about the graph. And this, before it was local max, and then now this is the shape and the turning of the tangent line. Maybe look at the curve of it. So, let's do a trig one. Any questions on this one though? Let's see, we're on 0 to 2 pi. Now, as you can imagine, sine of x is like this, so it'll certainly have some like concave up, concave down areas, max and min as well. So just a basic function like this is a good one to look at. We're just going to be on 0 to 2 pi. So first, increase, decrease. Let me just do the first derivative, just cosine A. So I set it equals 0. This one is basically all unit circle. So I'm looking for where the cosine, the x values are 0. Right, like right here. Pi over 2, and we would also include down here 3 pi over 2. Those would be our critical points for this one. Okay, and so then I just, make a number line. Let's see, pi over 2, 3 pi over 2. So you just got to choose carefully here. I want a value in between. I'll select pi. It's between pi over 2. Right, so unit circle, I want pi over 2 to 3 pi over 2. So I'll select pi in the middle. Let's say on the left of pi over 2, I can select any of the other keys, pi over 6, pi over 4. So, how about, let's see, for cosine, pi over 3 might be an easy one. Any of them will work. All we need is the sign. So. And to the right of 3 pi over 2, so I need something in the quadrant 4. So any of the key trig values, but just in quadrant 4. 5 pi over 3, 11 pi over 6, 7 pi over 4. Pretty much the ones you want to choose. So I will write down that I'm looking at the increase, decrease slopes. So I'm plugging this into the first derivative, which is right here. Let's start with pi. Cosine of pi. Cosine of pi right here. -1, right? That's second I was thinking 0. That's fine. So it's negative. That's all we need. Let's do pi over 3. Cosine pi over 3 right here. Well, everything is positive in the first quadrant, but it would be 1/2. So, but positive. And then down here, the choices weren't that important. It's just down here, cosine is positive. Cosine 5 pi over 3. Again, as you can see, it doesn't always alternate, but yeah, a lot of times it can. But just don't, you gotta check, it does not always do that. Okay, so then we can write down it's increasing and decreasing. I'm gonna get rid of these test values. It's increasing where it's positive. Now this was not negative infinity, it was 0 where we started. So 0 up to pi over 2. Union, and then we jumped over here, 3 pi over 2 to 2 pi. And then it's decreasing where it's negative, so that would be pi over 2 to 3 pi over 2. Okay. Now I'm just going to do the second derivative, and it's the exact same process. Hopefully you're just catching on with this. Same thing, but for concavity, second derivative. So second derivative of cosine would be, or just the derivative of cosine, would be negative sine. set it equal to 0, and then I'll take one step to divide by -1. Divide both sides by -1. So 0 equals sine of negative.
What did you do?
I just divided both sides by -1 to get rid of the negative sign. Then just as before, sine of what value is 0? Let's see. I think right here, 0 and pi. However, 0 and 2 pi, same thing. They are not in the interval. So we're only going to want pi. That's where sine, the y value, is 0. Well, it would be -1, 0. So we're just going to do pi.
Why is it 0?
It's just not in the interval because it's a it's not a bracket, it's a parenthesis instead of a bracket.
Also doesn't include it.
Right. So we don't include 0 or 2 pi, just pi. I do number line. So here's pi. We can just plug in any value on the right and left. So how about I just plug in, and I can even do like 3 pi over 2 now. How about I stick with this? Let's just do like pi over 6 here. Okay, just any of them really are going to work. So I plug this into the derivative, the second derivative. Now notice it's this one. Okay, don't do the final one. It's actually divided by -1 on that one. Okay, so it's going to do the original or an equivalent version of the original. This one would not be. Okay, so let's plug in pi over 6. It would be negative, and then sine of pi over 6 is a half. So basically we get a negative number. And then 3 pi over 2, so it would going to be negative, and then sine of 3 pi over 2 would be -1 down here. So it'd be negative of -1, which is positive. Okay, so now I can finally write my concave up and down intervals. Concave up just where it's positive, and then we get rid of the test values. So the interval is pi, starting with that. So positive pi to 2 pi. Pi to 2 pi. And concave down. Where it's negative, that was 0 to pi. Okay. So you look up here, I mean, there's a lot going on. You're writing intervals, points of we could do local max and min, increase, decreasing. You just gotta be careful, do the derivatives correctly, plug them into the right spot. Some of the work isn't too bad, it's just knowing where to go and where to plug it in. Well, anything I can answer on that second one? No? Now, I want to tell you, I kind of mentioned this point a little bit already. In the last example, the concavity, this one over here, changed at pi. It was negative concave down, 0 to pi. It was concave up, pi to 2 pi. And we call this a point of inflection. So similar to critical points for first derivative, we call this, for the second derivative, a point of inflection. Now, it's only where concavity changes. So you'll continually hear me say, like, before here, we got x equals pi. I would have said that's a possible point of inflection. Because we have to see if the concavity changes in order for it to actually be a point of inflection. Let's see. So one side is concave up and the other side is concave down. So just like a critical point, it's actually an ordered pair. But we usually just look at the actual coordinate of that critical point, of that point of inflection. So this one actually includes where the second derivative is 0 or does not exist. We'll normally just get the first case. So let's try it for this one here. We saw up on this one, it changed. at pi, so that one was a point of inflection. Let's find all possible points of inflection for this one. This, I have to just directly go to the second derivative. So I'm going to do the first derivative. 15x to the fourth minus 20x cubed. Okay, now I didn't ask about local maximum or critical points, increasing, decreasing. So I go on second derivative. 60x cubed minus 60x squared. So possible points of inflection are where the second derivative is equal to 0. So when set it equals 0, I will factor. In fact, go to 60 and an x squared. DCF. So I'll be left with x and then 1, minus 1. So here I get 1, so x minus 1. And here I'll get 0. I'll get 0. Right, I'll divide by 60 and get, divide by 60 and get 0 on both sides equals x squared. And then do a square root. We get plus or minus 0, which is just 0.
Is that all?
You have to check. So we cannot conclude these are these are possible points of inflection. The x coordinates of the points of inflection. So it doesn't mean for sure. We have to check concavity. So I'll do a number line checking second derivative, and I'll choose 0. Well, I'll plug in 0 and 1. Sorry. 0 and 1 are the possible points of inflection. I'll choose negative 1, 0.5, or half, and then 2. And I'll check and see. Let's see. Let's just for a little bit of time's sake here. So when I plug these, I plug in negative 1. I will get a negative value. When I plug in a half, I will get a negative value. And when I plug in 2, I will get a positive value. Okay. So I'm plugging these into the second derivative. All right, so what you can conclude here is there's only one point of inflection. So I'll put point of inflection at x equals 1. Not at 0, because the concavity was still negative. It did not change. So it was concave down up to 0. Then still was concave down 0 to 1. And then 1 to 2, it did switch. This might be another one just to look at the graph real quick. Okay, so concave down up to 0. Okay, so it's shaped like a frown up to 0. But you can see then it's actually like a local max. Then it's concave down some more. It's still shaped like a frown, but at 1. It's actually not at the minimum, right here. At 1, what if I get 1? Okay, basically about right there. Then it turns and becomes shaped like a cup. So it becomes concave up. So it was only a point of inflection at 1 right here. So again, shape of the graph, it changes concave down, concave up. That's what points of inflection tells us a lot about the shape of the graph. So what we notice, you can't just automatically say it is a point of inflection. You have to check the concavity. I'm not going to do part B. It's just similar. Similar to part A. So any thoughts about that right now? I want to do one more example, and what I'm actually going to do is a little out of order here. There's some graphical stuff we can do. I'm going to go to the next page after that. So flip to page 10. The graphical stuff, I think, well, when we come back from grids, that's where we'll pick up with this section. So I'm just going to jump right to the second derivative test to finish up. It really I could have put it after what we just did. All right, so second, guys, first derivative test, local max and min. If it's increasing on one side, decreasing on the other, it's a local max. So if it changes. Second derivative test is also for local extrema. It also helps us with local max and min. But it uses concavity, because that's the second derivative. So I say here, it can sometimes be an easier way to determine local extrema. Or sometimes it's just nice to do a different method. So instead of looking for sign changes, we evaluate the second derivative at stationary points. So here's what it says. If f prime of c, so at some x coordinate c, if the slope is 0, and, let's translate this, f double prime is less than 0, concave down. So it basically says this, if it's concave down on this interval, shaped like a frown, but at C, the slope is 0. It's a critical point. Local max. Right? So again, sometimes it's better to think about it conceptually. Second derivative less than 0, that means concave down, shaped like a frown. Well, if we know at that, it's a critical point then that's going to be a local max because the slope is 0 and there's a hill. So it doesn't always have to happen, it could be concave up like that, but then concave down. It doesn't have to be a max, but if the slope is exactly 0 on that interval, then we do know it's a local max. And just the reverse is true for the local min. If we know it's concave up, shaped like a cup, then at C, the slope is 0. Then it's local min. Do note that the test fails if the second derivative is equal to 0, or if the second derivative does not exist. It will fail. I say here, if the first derivative is tough to work with, the second derivative can be a better option. Or if the second derivative is difficult to find, use the first derivative test. So now you're just going to have two options. Okay, so let's do one example of this. Use the second derivative test. Find the local max and min of this function. So it tells right there I gotta do the second derivative. So first derivative, 3x squared minus 12. Second derivative, go here. Second derivative is 6x. So what I need is, I need to know where the critical, I need to know C. C is a critical point. Okay, so I did first, second derivative. I need to know where C is though. Alright, so I need to know, this says right here, when f prime is equal to 0, this is critical point. So let's go to the first derivative and get the critical points. Alright, we set this equal to 0. I'll go ahead and factor out of 3. There's different ways to solve this one. Get x squared minus 4. And then I can do difference of squares to make it x plus 2 or x minus 2. And so I get 2 and negative 2. Because 3 does not give me any solutions. So I know those are the critical points. Now let me go up to the second derivative here. It says, if we know at C, so f double prime, the second derivative at C, if it's negative, if it's less than 0, concave down, then we will know it's like this, and it'll be a local max. If we know the second derivative at C is positive, concave up, it's shaped like a cup, it'll be a local min. So this one, what I do is I need f double prime of my C value. So here's a slight difference. I'm not saying it equals 0. F double prime, I'm checking each of these. So we'll start with 2. let's see. So I plug in 2 to the second derivative here. 6 times 2 is 12. So what that tells me is it is positive, it's concave up. So basically it's shaped, it's concave up, and so at C, the slope was 0, it's a local min. So I'll just put local min at x equals 2. I'll do the second derivative at -2. This will be 6 times -2, which is -12. That's a negative number, so it's concave down, shaped like a frown. And so at this point, it looks like this one, where it's concave down, shaped like a frown, and the slope was 0. So it's a local max. So local max at x equals -2. And finally, the chart below just illustrates some of these differences. It tells you, all right, here's y double prime, y double second prime. Here's inflection, here's increasing, decreasing, and it kind of gives you a little summary of that. So does the next page, actually. So first, questions on this one, second derivative. You'll notice some differences where you're not setting this one equal to 0. You plug your critical point in and look at the concavity, the concave up or down. Okay. There's a little summary. There's also on the next page. Oh, anyway, it's at the end of the thing. There's, well, on your page, there's if you turn to page 11, there's a summary of all this. There's a summary example of all this. Okay. Let's work for a little bit. I know we don't have as much time as I wanted, but let's work for a little bit today, and then tomorrow we're going to work on the practice or concavity. So I should say monotonicity and concavity. Just say monotonicity and concavity practice. Let's work on that for a few minutes. I'll be around to help out as well if you need it. One second. Yeah.